Okay, so now we're going to go through chapter 25. We're going to cover a lot of chapter 25, but not this last section, section 5, which deals with capacitors and circuits. So we're just going to cover most of the first 4 sections. Okay, so the first thing we're going to do is introduce a new quantity called the electromotive force. Okay, and electromotive force, we use the abbreviation EMF for short for electromotive force, obviously, and we use this kind of curly capital E for the symbol. Okay, so here is a new quantity. So what is it? The really annoying thing about the electromotive force, the EMF, is that in spite of the name, which has force in it, it is not a force. It is not measured in newtons. So what is it? Okay, let's say you have a battery. Here in an electrical circuit, this is the symbol that we're going to use for a battery. And a battery is just some object. You don't have to worry about what goes on inside the battery. All you need to know about a battery is that there are 2 connection points, 2 terminals. Here's one of them. Here's the other. And a battery maintains a constant, or tries to maintain a constant electric potential difference across the 2 terminals, from one side to the other side of the battery. Okay, so we can use a device called a voltmeter, and what a voltmeter is a device where you have one wire, you connect it to one terminal of the battery, for example. You connect the other wire of the voltmeter to the other terminal of the battery, and what it will do, not surprisingly, is measure the voltage, the potential difference between the 2 terminals of the battery. Okay, so what the EMF of a battery is, so we're going to use EMF as a way of describing a battery. It's a property of the battery. It is simply the potential difference between the terminals of the battery if the battery is not connected, and therefore there is no current actually going through the battery. Okay, so it's possible for current to flow. If this were a complete circuit loop, it's possible for a current to flow around this loop and therefore through the battery. But if the battery is not connected to a circuit, if it's disconnected, then there's no current flowing through it, and the potential difference is delta V is simply going to be equal to the EMF. I know it looks like we complete a circuit here by adding a voltmeter, but voltmeters are designed to not draw any current through the battery, or at least very minimal current, so you can pretend there's no current going through the battery when the voltmeter is attached. Okay, so that's one way of thinking about the EMF. Another way is this. You could say, okay, let's say you have a closed circuit. So what these black lines indicate here, these black lines and this black line over here, think of that as a wire. This symbol here represents a battery. This symbol here is a resistor. So that's how we represent a resistor in an electric circuit. So it's a piece of conducting material. It's connected on one side to a wire, connected on another side to the wire. Typically, we neglect the resistance of the wire itself. Wires do, of course, have some resistance, but if we add a resistor to the circuit, typically this resistance is much bigger than the resistance of the wire, so you can forget about the wire resistance. Okay, so if you construct a circuit in this way, the battery is going to push a current around this circuit. Okay, so the current is going to flow through the wire, it'll flow through the resistor, through the wire again, and through the battery. Okay, so we talk about ideal batteries in electric circuits. An ideal battery is one where there is no so-called internal resistance. And what we mean by that is, well, a battery is made up of conducting material. That conducting material will have resistance. That's how it is for a real battery. But often it's the case that the resistance in a battery is so tiny that you can just forget about it. Okay? Just like we can often forget about the resistance in the wires of an electric circuit. So if you have a circuit like this, and you pretend the battery is an ideal battery because the internal resistance of the battery is so small, then when you use a voltmeter to measure the potential difference across this battery, even though there's a current going through it, the voltmeter will simply measure, well, it'll measure a potential difference which is equal to the EMF. So there are a couple ways you can conceptualize what the EMF is all about. Okay, so moving on to the next page. The EMF is not a force, as we said, because it has units of volts. So question is, what causes this potential difference? Okay, not surprisingly, potential differences are associated with electric fields. So this symbol here for the battery, I didn't mention it earlier, I will now. The long line represents the high voltage, the higher potential side, and the smaller line represents the lower voltage or lower potential side of the battery. So let's say this is our battery over here. It just looks like a box. We don't really care usually when we're solving electric circuits problems what goes on inside a battery. But in case you're wondering, what ends up happening is there's some kind of mechanism. It's usually some kind of chemical reaction, depending on the kind of battery you're talking about, which will push positive charges to one side and push negative charges to the other side. Okay? Don't worry about what this mechanism is. There's some kind of chemical reaction, the result of which pushes positives to one side, negatives to the other. And what this does is it creates an electric field. Positive charge over here, negative charge over here. Electric field points from positive to negative. So in this figure, it points to the left. And if we have an electric field present, well, we know there's a potential difference associated with that field. Okay? And the rule is, if you go in the direction of the electric field, the electric potential decreases. So this will be the high potential side. This will be the low potential side. So you have a high potential and a low potential. Okay? So this is what happens inside a battery. Okay? Again, there's lots of details that I'm skipping over here because it doesn't concern us for this course, but this is what happens. So the EMF source, right, which is the battery, and more specifically the chemical reaction that causes the battery to have the properties it does. This EMF source has the effect of carrying positive charges from a low potential to a high potential side. It goes against the direction that charges would normally want to go, and carries negative charges from a high potential side to a low potential side. So that's what's actually happening here. Now, in both cases here, that corresponds for these two different types of charge transport to carrying charges from a low potential energy to a high potential energy. If you have a pen and paper now, just write down this equation, which is U equals Q times V. Okay, that's an equation we've seen before relating electric potential and electric potential energy U. Okay, obviously, because of the sign difference, it means that if you increase the electric potential V, you're going to increase the potential energy if Q is positive. Okay, but if you go from high to low V, you decrease V. Well, in that case, if you multiply that change in potential with the negative charge, you will also be going from a low potential to a high potential energy. Okay, all that to say, there's some kind of source of energy that deals with this charge transport. Okay, so as charge moves through the battery, the potential energy increases for both the positive and negative charges, which may be transported inside the battery. For this reason, because we're pushing charges from a low energy to a high energy, we call the EMF source a charge pump. We're pumping charges from a low energy to a high energy. Okay, that's kind of like a water pump where you can lift water against a gravitational field from low potential energy, gravitational potential energy to high gravitational potential energy. Similar sort of thing here. Okay, so the actual definition of the EMF, E, is the work done per unit charge to move the charges across this EMF source, the EMF source being the battery. Okay? In a conventional battery, where does the energy come from? I've already said, typically it comes through chemical reactions. Okay, now, if you have a battery connected to a resistor and a current flows, as in this picture here, okay, the battery will tend to heat up just a little bit. You may not notice it, but if you do a careful measurement, you will discover that it heats up a little bit. Why does it heat up? Because of this thing that I've called the internal resistance. A battery is a conductor. Conductors have resistance. Batteries are no exceptions. Okay? So we can model a real battery. So that's this dashed line in this picture. You can model a real battery as an ideal battery, where I use the battery symbol down here, connected to a resistor. And the resistor is the internal resistance, R. Okay? It doesn't actually mean if you open up a battery, you will discover an ideal battery connected to a little resistor. Okay, this is just our way of picturing the internal workings of a battery. Okay, so if we have an electric circuit, what happens? The current is going to flow from the high potential side of the battery. So put a little, positive sign should be up here, but the negative sign should actually be down here. I don't know how that negative sign, so this negative sign here should be, negative sign should be down here, sitting beside the A. Okay, so anyway, a current is going to flow. In this case, it's going to flow clockwise because it's going to come out of the high potential side. How do you know it's high potential? Look at that big line for the battery. There it is. That means high potential. And then outside the battery, it will flow from high to low. Outside the battery, it flows from high to low. Inside the battery is different, but outside the battery, I'll say it again, flows from high electric potential to low electric potential. Okay? So, so the current is going to go through the battery, obviously, and it's going to go through this resistor. And here's a nice way of visualizing what's going on. You can imagine, let's say I start at point A, and I go through, I just take a little walk around this circuit. If I take a little walk around the circuit, I end up back at A. Okay, well, let's say I kind of lay out the circuit in this sort of linear configuration. Now this point at the very end, here's point D, is actually connected back to point A. So I've not put in that final stretch of wire that connects these two sides, but good enough for what I want to use this to explain.